Richard is a retired civil servant whose career has been divided between academic research in pure mathematics and its application to cybersecurity. He was the founding head of research at the Heilbronn Institute and has also served as vice president of the IMA. In the first half of his career, he was an academic at Cambridge University. In the second half of his career, he was a mathematician at GCHQ. In the third half of his career, if I've done my maths correctly, we call that retirement. He now consults still for the Heilbronn Institute and does a variety of other outreach, including this talk this evening, which we're very grateful for. So, ladies and gentlemen, Richard Pinch.
Thank you, Sam. Thank you very much for the invitation. It's a great pleasure and an honour to be here. What I hope to do in this talk is to talk about codes and coding under three different aspects. I'm going to talk about coding as being a synonym for programming. I'm going to talk about codes, which are ways of making messages hard to read. And I'm going to talk about codes, which are ways of making messages easy to read. And what I want to do is to show how all of these things come together and have been brought together by what I call the postmodern era in cryptography, the quantum internet era. So let me hope. Yes. I have 76 slides, and at 2 minutes a slide, I hope to get a bit faster than that. But it will be necessary for me to talk about a wide variety of things, most of which I don't really claim to be an expert in, and first of those very much so. So what I'm going to do in this year of quantum is to say a bit about quantum physics, a bit about computing and about quantum computing, more than a bit probably about cyber, by which I mean cybersecurity, and by cybersecurity I mean cryptography. And I want to say what the quantum era, effect the quantum era is having on that. I want to talk about codes for making messages easy to read, and quantum codes for making quantum messages easy to read. I want to talk about how they affect the postmodern era in cryptography, and I want to make a few remarks, and by that time I hope we might have time for a question or two. I've just said all that. They make me say this. This talk doesn't represent anyone. His Majesty's government now wants my opinions, it can't have them. And I've taken images from a wide variety of places. I shall attempt to acknowledge them as I go through. So let me talk about quantum physics. So let's go all the way back to the 19th century. So at the end of the 19th century, classical physics was in crisis. Classical Newtonian physics works extremely well for predicting medium to large scale phenomena. It's very good at telling you exactly what angle to elevate your artillery piece to if you want the shells and the bombs to fall on the other side. And it's pretty good for predicting the movement of planets and for discovering new planets by looking at the deviations that the existing planets have or had from the predictions of Newtonian physics. But it didn't account for the anomalous precession of the orbit of Mercury. The anomalies in the orbit of Neptune, for example, were attributable to another astronomical body, which was discovered and is called it's Pluto. I may say incidentally at this point, When I was at school, there were 9 planets in the solar system and none at all in the rest of the universe. Now there are 8 planets in the solar system and thousands in the rest of the universe. So that is, I suppose, some sort of progress. Equally, thermodynamics works well for predicting the behavior of steam engines, which was really quite important in the 19th century, but doesn't account for black body radiation. Just black body radiation just doesn't work. And Maxwell's equations, which were becoming practically important, worked very well for predicting the behavior of light and electromagnetic radiation like radio waves, but are not compatible with Newtonian physics because they appear to postulate an absolute frame of reference. And the Michelson-Morley experiment showed either that the ether, the putative medium that transmits electromagnetic radiation, either doesn't exist, or if it does, then it turns out that the Earth is absolutely stationary at the center of the universe. Neither of those were very healing propositions. So the resolution of these crises came with quantum physics. Physics are very small things, and relativity, which is physics, a very big thing. Classical physics is a very good approximation to each of these theories, but they are still incompatible, and there's still no known overarching theory that encompasses them all. So mathematically then, at the beginning of the 21st century, physics remains in its state of crisis. And if I were a physicist, which I'm not, and I'm extremely apparent, no doubt, I wouldn't be able to sleep at night. However, these two theories work extremely well in their own area. And the important thing is that we can build technologies on top of these theories. So general relativity is really good at telling us how to launch space probes to other planets and get them there, which is a very, very powerful test. And the physics of the very small allows us to build quantum devices which work and do what they're expected to do, and in particular, quantum computers. So quantum technology, which is not just quantum computing, it's mainly quantum sensing, actually. It's much more economically, currently much more economically attractive proposition. The UK government over the last 10 years or so has invested about between £0.5 and £1 billion in a quantum technology program across various hubs, numerous industrial partners. Quantum computing is a topic within quantum technology, the one I'm interested in, and quantum cryptography, better called quantum secure communication, and post-quantum cryptography are topics within quantum computing. And so what I'm going to talk about really is a niche within a niche within a niche, but there's quite a lot of that. So one way of viewing quantum physics is, in this city, I think it's fair to say, the Oxford approach to philosophy is to ask or to focus on what statements or questions is it possible to make about something. And to me, the important thing in quantum physics is to say that not every question that you might want to answer can possibly be answered. There are some things that you just aren't going to know. Mathematically, we can regard physical phenomena as existing in a superposition of states. A superposition is some statement about the possible states and about the probability of an observation when you interact with that state. Before you interact with it, it just exists out there somehow, and you can't say anything about it because you haven't interacted with it. What you can say is what is likely to happen when you do interact with it. So you make an observation, you measure some physical property, you actually interact with that, and what you will get, therefore, is a random sample from the probability distribution that existed while the state was still unknown to you. And as an example of the not all physical properties can be measured in a single observation, Heisenberg's uncertainty principle, that just says there are some questions which you can't ask. I cannot know, so I want to get on to, yes. For example, I can't know the position and the momentum of a particle exactly at once. It's just not a question that I'm ever going to get an answer to, because to observe its position, I have to interact with it by throwing things at it or prodding it with a stick, and that will perturb its motion. And that means that whatever information, I've started to degrade the information about its momentum. This is similarly with energy and time. You can't, on a very short time scale, sorry, I'm in the right way, there we are. Very short time scale, we can't say we don't have conservation of energy. That sounds odd, but the Casimir effect demonstrates this. The Casimir effect says if you've got a vacuum, then there will be fluctuations in the vacuum in which electrically charged particles will briefly come into existence and disappear on a certain time scale. And if you've got two metal plates close to each other, the induced charges on those metal plates will be measurable because they'll give rise to an attraction. So in quantum physics, these two metal plates in a vacuum will actually be subject to a mutually attractive force, which can be measured. And if you measure it, it's there. And this is a genuinely quantum effect. It can't be explained in terms of classical physics. I skipped over, but I really have to show you, say something about Schrödinger's cat. This is the well-known thought experiment. You have Schrödinger puts his cat in a box with a device that randomly decides whether or not to release some poison gas into the box, and in such a way that the probability of the cat being alive when you open the box again is a half. So what is the status of the cat inside the box? And the best answer I can give to that is this is not a question you will ever know the answer to. It is tempting but fallacious to believe that there's some real status of the cat, which somehow, if only I was clever enough, I could know. And in the mathematical models of quantum physics, just make it clear, this is not a state, an eigenstate in the jargon, that you are ever going to be able to access. When you open the box, the measurement you make affects what is in the box. It causes it's to connect back to the rest of the universe, in particular you and your measurement device. So, and the electron diffraction through slits, a famous experiment, shows that electrons do not behave like classical particles. They are not billiard balls. When you fire them at a diffraction slit, they behave as if they're waves, but what these waves are measuring is the probability of measuring the electron in a particular location. It's probably not useful to think of the electron really going through one slit or the other, so much as what the probability is of that, if you were able to measure it. Okay, so I'm very briefly going to describe the mathematics of superposition. Suppose we have some atoms in a crystal lattice and they spin either up or down. And if I've got 3 such atoms, then there are 8 possible pure states, all pointing up, through to all pointing down. And so a superposition is just some linear combination of these. So these are just states, they're just formal objects. As formal objects, I can just add and multiply them by scalars. And those scalars encode the probability of that being the state that you find when you measure the system. If you already know that they're all up, you'll just get the pure state, which is 1 times up, 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 and 0 plus 0 times everything else. But if you don't, you'll get a mixture of those states. And that leads to the possibility of correlation or entanglement. Suppose the state, this is the state in which with equal probability they're either all up or all down, but we don't know which. We do know that they're all the same. That's what this state encodes. So if I now take one of those atoms and keep it in my laboratory and send another of those atoms a long way away, now I decide to measure my atom, be either up or down, I now know that the other one will be the same. Now, does that mean that my action here has caused something to happen over there? No. Einstein called this action at a distance, or sometimes spooky action at a distance. It's not a useful way of thinking about it. And if I had an entire lecture to talk about it, I would talk about Bell's inequality and why this isn't, why there is no action at a distance here. But exactly what's going on here is a philosophical debate. And the important thing is that entangled states exist in nature and can be created, manipulated, and used in the laboratory. So it's a brief, very brief introduction to quantum physics. I'm apparently going to change tack, but actually I'm not. Just coming at it from another direction. I'm going to talk about computing. I feel slightly nervous about doing this in front of this audience, but bear with me. So Alan Turing, in the 1930s, interested in questions in mathematical logic, proposed the notion of the Turing machine. It's an abstract model of computation. It has a store, which is the tape. It has a finite program which controls the machine, and it is in various states. It scans the tape and reads and writes onto the tape, depending on what state it's in. This is the Church-Turing thesis. So here I have, this is the statue of Alan Turing at Bletchley Park, and a photograph of Alonzo Church, who was at Princeton. Alan Turing went to Princeton to work with Church in the 1930s. The Church-Turing thesis is that this model precisely captures all notions of computability, and that every computer ever built is, in some sense, a Turing, an instance of a Turing machine. I want to explore that thesis in the next 40 minutes or so. Working with Alan Turing at Bletchley Park shortly afterwards was Tommy Flowers, who built the first, let me get this right, it was the first electronic digital stored program general purpose computer, Colossus. It was general purpose, although it was used, it was built, designed and built for a special purpose, namely solving high-grade German diplomatic ciphers, the Lorentz cipher, known at the time as Tunny. It is a general purpose machine, and I have seen Colossus output in which it was used, for example, to compute and print out statistical tables. It's perfectly capable of doing general purpose numerical calculations. It's a general purpose computer. There is a mythology, incidentally, that after the end of the war, Colossus was smashed to bits on the grounds that we wouldn't need anything like that ever again. I can tell you that statement is entirely untrue. In fact, several colossi were built by the end of the war, and at least one of them was still in service in the 1950s. People who built it knew very well what they'd got. They just didn't choose to tell anyone else about it. Programming, coding, that sort of coding, actually curiously goes back earlier than the first working computer. We see here a rather grumpy-looking Charles Babbage towards the end of his life. He had failed to get government funding for his differential engine and analytical engine, partly because, as still happens today, he had not been very good at applying for government grants. His argument was very roughly, this is frightfully clever, so you should give me a lot of money. Arguments of not much more sophistication continue to be deployed today. And of course, the lady on the right is Ada Lovelace, who was, I think, probably had a clearer insight into what programming was all about, perhaps than Babbage did. Certainly was his equal in the field of programming the engine. Another myth, incidentally, is that the analytical engine could never have been built because it was beyond the scope of 19th century technology. That's not true either. The Science Museum did a project some years ago to reconstruct pieces of it using only available technology, brass, mahogany, cast iron, steam, etc. And yes, it works fine. It just would have been jolly expensive. And Ada Lovelace is sort of famous for having said, the analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. And Babbage actually is on record as having said that he occasionally got asked whether his engine would produce the right answer if it was given the wrong input. And he said he did not know how to answer that question because it betrayed such a misunderstanding of what the analytical engine was all about. I invite you to consider whether these statements remain valid in the era of artificial intelligence and large language machines. But that's not what I want to talk about. It is true that programs may be randomized. That's to say, there may be conscious random elements, conscious randomly generated data as part of the algorithm. And so it's reasonable to think of results as being probabilistic, although there are very, very real concerns about standing behind computer calculations that we do not understand and cannot verify or repeat. However, Richard Feynman was one of the first people to suggest the application of quantum states to computation. That's a stamp, a US stamp with Feynman and some Feynman diagrams on. I don't think they've got anything directly to do with computing, but he identified, for example, that quantum state transitions in a quantum analog of Turing machine, for example, would have to be different. Information in the quantum realm has to be preserved, so a different set of state transitions would be required in a quantum computer. So let me just very briefly talk about what a quantum computer a la Feynman would look like. I'll just remind you that in a modern classical digital computer, the store universally now consists of discrete bits 0 and 1 represented by some physical states, which move through circuits which perform Boolean operations such as NOT and AND. In quantum circuits, the store consists of entangled bits. So a quantum register, well, I showed you a 3-bit quantum register instantiated by atomic spin. The state of the register is a superposition of states. These quantum states move through the circuit, through quantum circuits which perform unitary operations, which include some but not all Boolean operations. and some others. And I'll just mention the so-called square root of naught operation. This sends the pure state 0 to a linear combination of 0 and 1. And it sends the pure state 1 to a different linear combination of 0 and 1. The matrix is unitary, that's to say its inverse is equal to its transpose, sorry, to its Mission conjugate. And if you apply this twice, you get the identity. You always get back to the original state. This is clearly not a classical operation of any kind. There is no classical operation, which when you perform it twice, gives you Boolean negation. So we lose some Boolean operations and gain new, genuinely quantum operations. So a quantum computer consists of quantum registers and quantum circuits that process the bits that are stored in the quantum register. So computation consists of preparing the states, that's to say, setting up these superpositions, feeding in the data, and interacting with it to observe the result, reading out the answer. And a way of doing that is to arrange the computation so that the correct answer emerges with very high probability and the wrong answers all have very low probability. So this is a genuinely probabilistic paradigm. If you can do that. Right. Now, I just want to show you a film, which is a film of somewhere very cold. Anyone recognize it perchance? This is the surface of Pluto, that planet, our minor planet. I will play it again. You can see there are white bits, sort of reflective bits, and that's snow. It's nitrogen snow, solid nitrogen. So the temperature on the surface there is about 30 Kelvin, or minus 240 Celsius. And so that's a very cold place. So here I have sort of today's not exactly trick question, but question for the audience. Would you like to say where you think the coldest place in the universe is? I mean, the surface of Pluto would be a good candidate, but it's 30 plus 33. I mean,
in a quantum computer? Guessing?
Yes. Here it is. A good candidate for the coldest place in the universe is just around the back of University College in London, in this fridge. I mean, this is a fridge of a proprietary device. It is probably around millikelvins in temperature. Outer space is far hotter than that, about 3 Kelvin. Because to get these quantum effects, to prevent them being instantly decohered by thermal vibration from the rest of the world, you have to get it really cold and really well protected from the rest of the universe. And you can do that. And then you have to be able to get some kind of electronic signals to and from that state. And that's a really, really smart piece of technology. I have no idea how you, well, I mean, I have some idea. You go up in sort of basically in logarithmic stages. Every layer is 10 times hotter than the previous layer. And you very cleverly pass messages. But it's very hard. And you have the problem of thermal vibration, because even at that temperature, there's some thermal vibration. And you have interference from cosmic ray particles, which just zap in all the time and just occasionally pass through your device and hit something. So the technology, about which I know very little, is extremely challenging, but we can do it. We have the technology. And here is a picture of a quantum computer. This is or rather a quantum circuit. And of course, it's the picture of the fridge, not the circuit. The circuit is in there somewhere. It's about 80 bits of quantum bits. And it's part of a network of quantum circuits run by IBM. This one is actually on display in the foyer of one of their offices in London, but it's a working device. It's not just a mock-up. And you can rent time on this if you want. So these things are here. So quantum computing, it's not a new paradigm in computability, because quantum circuit could be very elaborately simulated by a classical system involving complex numbers, but it's very definitely a new paradigm in complexity. It's very good at calculating certain kinds of things that are very hard to do classically, and thereby hangs the tail. There's a very rich class of problems. One of them is brute force search. There is a quantum algorithm for solving brute force search problems called Grover's algorithm. And there is a quantum algorithm for factoring large numbers called Shor's algorithm, works in quantum polynomial time. And there's another, there are very, very few essentially quantum algorithms, and there may be a fourth one to put on the list, but I don't have time to discuss that. There's one called soliloquy, which was discovered by colleagues of mine at BCS or rather at the Heilbronn Institute around 2007, and which was declassified in 2014. And it's thought to be polynomial time, but it is. It finds hidden structure in lattice problems. So a brief excursion here. Around 2005, I was one of the most junior people sitting around a table talking about BCHQ's policy towards quantum computing. And one of the questions was, when will quantum computers come online? And so I said, I think we should plan for 2017. And somebody said, do you really believe that there will be a quantum computer online in 2017? And I said, no, but I do believe that the hype around quantum computing will have got onto the front page of the Times, and you will be getting phone calls from the minister saying, this quantum computing thing, what is GCHQ doing about it? And your answer needs to be, well, Minister, we started thinking about it 10 years ago. And the answer is, well, soliloquy was part of the answer. What we discovered, the other thing we discovered, far more importantly, was that smart as the people at Heilbronn Institute, researchers at Heilbronn Institute were, they're not as smart as the rest of the world put together. And it was probably the right thing to do was to publish our results and stimulate research in the area rather than trying to just beat the rest of the world. Shame, but that is. Okay, so practicalities, quantum algorithms assume the existence of logical qubits. That's to say, quantum bits that exhibit perfect quantum behavior and can behave perfectly in quantum gates. That's not going to happen. So we need multiple physical qubits, multiple atoms spinning together to absorb the interactions with the rest of the universe. So this requires new forms of error correction. Quantum errors are different to classical errors because quantum bits are different to classical bits, such as surface codes. And the mantra here is, if you're designing an error correcting code, you need to understand very well what the nature of the errors are that you're trying to correct. So I just want to say something about quantum devices. So I'm interested in quantum computers, which are things with quantum registers, quantum circuits that compute things. A lot of people are building quantum optimizers. That first fridge is in a quantum optimizer. That's to say, a device that uses quantum physics to solve optimization problems may or may not be completely general quantum Turing device. And quantum simulators. That's to say, quantum devices that simulate certain kinds of probabilistic behavior, which are not computations. And I'll say a bit more about that at the end. Okay, now the third strand is to talk about cyberspace, introduced by William Gibson in his science fiction novel, a consensual hallucination experienced by billions of operators in every nation. And you'll notice, incidentally, that he assigns foundation of cyberspace as mathematical concepts. We have a slightly different view of it now, but it's sort of a picture of cyberspace. It's a picture of the internet a few years ago, in which each country is shown proportion to its number of internet connections. You'll see, incidentally, that the biggest country in the world is China. The UK is pretty big, but tells us something. National security strategy categorizes cyber attacks as a tier 1 threat. Say it's as disruptive as international terrorism, blowing up tube trains. Real, it's growing, etc. So, brief history of cryptography. Okay, so traditional cryptography, secret key cryptography, traditionally goes back to Julius Caesar. Caesar cipher is the write the next letter but 3 in the alphabet. It was regarded as 24-letter alphabet. It was regarded as the next best thing to witchcraft at the time. And some cryptographers in the late Middle Ages were actually denounced to the Catholic Church because codes they were breaking were supposed to be so secure that it was impossible to break them except by witchcraft. Well, I don't think I'm giving too much away to say that that wasn't how it was being done. And it's an important strand in modern cryptography today. Modern cryptography is another way of saying public key cryptography, which was discovered by erstwhile boss Cliff Cox in 1972, and rediscovered shortly afterwards by Rivest, Shamir, and Edelman, RSA. Of course, is fundamental to internet communication. Another myth was that BCHQ invented public key cryptography, but had no idea what to do with it, so they just didn't smash it up into bits, but they just ignored it. That's not true either. They knew very well what was invented and used it very well, but I'm not going to talk about that either. And then there is postmodern cryptography, quantum and post-quantum cryptography for the quantum world. So traditional cryptography achieves a number of things: privacy, authentication, integrity, non-repudiation, and it depends on sharing a common secret key. So how do we do this? Well, if we need the secret key to set up a secure communication channel, how do we communicate the secret key without having a secure communication channel? Well, here are a couple of answers from different time periods. On the left, that is Mary Queen of Scots' codebook. I don't know if you can see very well, the words in there are things like names of people and places, and they all have arbitrary symbols or letters against them. And if both parties have got a copy of this, then they can communicate hopefully securely. It was exchanging things like this that quite literally lost Mary Queen of Scots her head. On the other slide is a one-time pad printed on a silk scarf in water-soluble ink and issued to RAF pilots during the Second World War, so that if they were shot down in enemy territory but were able to find the resistance, then they would have a set of code numbers that would allow them to communicate back to London securely. Had to be water soluble because if you were captured in possession of one of these, you were a spy and you would be shot. So you had to, if you thought you were going to be captured, you had to dunk it very quickly into the nearest bucket of water or other similar suitable biological waste product. So another answer is this report, which is part of the title page report written by Cliff Cox, what was then called non-secret encryption. And as we probably all know, and I'm not going to go into detail, the user's secret is the factorization of large number. If you only know the large number, but you don't know its factorization, you can encrypt messages. If you do know the factorization, you can decrypt them, and you can also demonstrate that you know that factorization without having to give away the factors. For example, you can just endlessly decrypt messages. People can send you messages and say, decrypt that if you're so clever, and if you can consistently do that, it must be the case that you are the person who knows that secret. Unfortunately, Shor's algorithm is very good at solving factorization problems. So it is a serious, practical challenge, threat to modern internet communication. So we need new public key systems. We've been thinking about that. Some people say, do we need it at all? And leading methods proposed are based on error correction of various kinds. The message is deliberately garbled, and the recipient can correct the error sufficiently if they know something secret about the code, usually in the form of some hidden algebraic structure, which allows them to error correct garbled messages much more efficiently than someone who doesn't know that secret. There is also a physical method called quantum key distribution, commonly but wrongly called quantum cryptography. I'm afraid it's a marketing term. The answer to quantum computing is quantum cryptography. It's just such a natural marketing term. I prefer to call it quantum secure communication. It's really about putting a very strong link into your chain. Quantum key distribution 1.0 for the classical world is you can do it with polarized light. The idea is that if someone intercepts the message and attempts to measure the bit, extract the bit, then they will garble the message. So it's really about tamper-evident communication. If Alice and Bob, if Bob receives about half his bits correctly, the message hasn't been tampered with. Anything less than that, someone is on the line sampling the bits and garbling them every time they sample them. And quantum key distribution 2.0, classical quantum key distribution, says you create entangled pairs. Won't go into detail, but so various nations are experimenting with things like trying to create an entangled pair where one of the entangled elements is in your laboratory and the other one is in a satellite, somewhere you can't easily get to deliver more key material. National Cybersecurity Centre doesn't recommend quantum key distribution until we really understand how it works, and in particular, how we can understand the whole of system approach and cost these attacks. So it's not their favorite plan. I mentioned soliloquy. Now, I'm going to talk about codes. Again, error correcting codes. These are fixed length binary words. And the Hamming distance is between two words is the number of changes you need to turn one word into another. There are any number of books on the subject. I've randomly selected one to show you the cover page of. What happened, the reason that book exists is that Charles Goldie and I were having lunch together, and he said, I've got to give this talk on communication theory, but I don't understand anything about error correcting codes because I'm a probabilist. And I just said, oh, that's easy. It's linear algebra of the field of two elements. So he said, oh, would you like to give those lectures for me then? So it's another important life lesson I learned. So the parity check code, you just append a bit to make the block to make the number of ones even. You saw the parity check code in operation. It's actually also called the paper tape code. 8-track paper tape uses parity code. And so Colossus, one of the things you saw in Colossus was the paper tape reader. But very fast, probably the best paper tape reader ever made. And the next obvious code you think of is the repetition code or majority, best of three code. This can correct an error because if one error occurs in three, you just take the majority vote, and that will be the correct one. And a more sophisticated one, the Hamming 743 code. This is a code with 7 bits, 4 of which are message bits. In other words, I can encode a 4-bit message, 16 possible messages. It has 3 different sorts of parity check, and it has minimum distance 3. Like the best of 3 code, it can correct 1 error out of 7. Error correction constitutes finding the code word, the correct word that's nearest to the received garbled word. And this is hard unless your code has been cunningly designed. I'll skip this bit. And a lot of work in the late 20th century went into finding really good ways of finding error codes with a lot of structure, algebraic structure, which were good at error correcting. And so these are photographs also taken from New Horizon. That film that I showed you is actually a sequence of photographs taken by the New Horizon probe. It wasn't real time. Taken about 100 miles up, I think. That's the surface of Pluto in one of those pictures. This is the surface of Charon, the moon of Pluto. It really is that color, I gather. And I just want to emphasize what was involved in taking that. So the radio on board New Horizon, which you've seen there out of scale, it would just about fit in this room. The dish is probably a bit too big. But, so the radio transmits about that much signal. And it is 5 billion kilometers away. Also in the sky, when we're trying to detect that, is the sun. It's ever so slightly brighter and a lot closer. So NASA spend a lot of money on error correcting codes that could be transmitted by something that was powered with batteries. And what they did was they had 3 ground stations and a lot of computers doing a lot of error correction because they could afford that. Arrokoth, incidentally, was the next. It's turned out to be 2 rocks that had collided. New Horizon passed that a few years later. It's the furthest object from Earth that has ever been visited by probe. It's about 7 billion kilometers away. And New Horizon has incidentally reached the edge of the solar system, the hydrogen wall, and has run out not of battery but of money. So error correcting codes typically have really interesting structures, which may make them very interesting to people like me who are interested in combinatorics. Golay codes, style systems, these are cunningly chosen combinatorial objects. Now, quantum states have two sorts of error. The bit flip error, which are the classical ones, and the phase flip, where the number, the coefficient in front of the state changes. And these correspond to movements of an electron spin, say, away from the north, pointing straight up in two different directions. So we need to know what they are, and we can design quantum codes that do this. So the Hamming code allows us to build the Steen 713 code, and this has two states. So each of those formulae encodes a particular state, which, in other words, it's each of them is a mixed state. There is a state that might be 7 zeros or 1010 or ... equally probably. And the other state is the one that might be 111, 0101, ... It's a complement of that. And the Steen code allows you to correct a single bit flip error or a single phase flip error in which one of those pluses turns into a minus. So your 7 physical qubits allow you to create a circuit with one logical qubit that can survive one error. So now, how do we turn error correcting codes into cryptographic systems? We don't actually worry about the message. We encode the message on the error. We use the message to garble our word. And if we're really good at ungarbling words, we can recover the message. But if we don't know the secret that allows us to ungarble the word, it's hard. So this is the advantage that the owner of the secret has. So this fast decoding and hidden structure problem is an active area of research, because if you know that some big matrix has got some hidden structure, the question is, can we find it? It's like saying if we have a big number and we find its factors, well, that's a genuine mathematical problem, and we're betting on it being too hard for mathematicians to solve. And that's not always a good bet. So a couple of concluding remarks. How to read a press release. Well, that is the Gartner hype cycle. I won't say where we are for quantum computing, but let's just say that it's possible that we are closer to the peak of inflated expectations than we are to the plateau of productivity. I would like to feel that we are on the slope of enlightenment. There are lots of people working quite hard at quantum computing. But when you read an excited press release, our quantum device has exhibited quantum supremacy, ... it can do this, it can do that. Ask, what is it actually doing? Is it a quantum optimizer, which have been around for years, and they do jolly well at the things they do well, which are to do with proteins and drug discovery. They're worth buying if that's what you want to do, I guess. Is it a quantum simulator? Well, the answer to that is yes, because these are the quantum devices that you will find in most excited press releases, which are supposed to have done something or other better than any classical computer possibly could have done. The reason for that is they are not computing things, they're simulating things. This is different. Are they quantum computers? The answer is almost certainly not. true quantum computers which push quantum registers through quantum logic gates tend to be pretty small. And the other thing to ask is, our quantum device has so many qubits. Are they physical qubits or are they logical qubits? If you've got a quantum computer with 1,000 logical qubits in it, then I would like to hear from you. But you've got something, but that is not what we've got. So quantum computing isn't, well, it's not the end of cryptography, it's not the end of cybersecurity, it's just another stage in its evolution. Lots of people working very hard, standards bodies are evolving new standards, and as a mathematician, I'm pretty sure that mathematics will continue to be at the heart of this enterprise in the postmodern era, just as it has been for the last 90 years. And with that, I will conclude my talk and invite questions, comments. Thank you very much.
So we'll start in the room, and I will be keeping half an eye on our 21 attendees still on Zoom. So in the room, do we have any questions for Rich? Yes.
So sometimes I use Charles Babbage as a cautionary tale for my engineers. Classic case of engineering scope creep. He started designing different engine number 1, then stopped when he realized he could make a better one, different engine number 2, and he stopped when he realized he could make the analytical engine, and never finished that. And I often argue, in fact, that he put back computing by 100 years because the Royal Institute was so fed up with funding such programs that they refused to fund anything quite some time after that. I was wondering if we're falling into a similar trap with quantum computing, in that we know it can, we think it can do certain very specific things very well, but we're trying to get it to do everything as a panacea of computing. And every other press release is how it's going to change the world forever. Whereas if we sat down and focused and said, let's limit our scope to something we're confident we can address, we won't annoy the funding bodies for quite so long. Any thoughts?
Yeah, so the question was, Babbage tried to do too many things, start things before he'd finished the previous one. Yeah. Are we making the same mistake? I think the answer is no, we're not, because we is a much more diverse group of people. And I've indicated that there are different sorts of quantum device, some of which are already being successfully deployed to do specific tasks which are of practical and economic benefit. So I think the answer is we're not going to fall into that particular trap. I think we are the trap that Babbage didn't fall into was, I don't think that he overpromised. Possibly because he made a Lovelace and nobody really knew what a computer was capable of doing.
I don't think the Navy ever got its logarithm tables right.
No, I agree that the use case, there was a very good use case, but it didn't achieve that. I think the trap we're going to fall into is a trap we're more likely to fall into is the overpromising, that it will do everything, that one device will do everything that anyone could possibly ever want to do. Well, yeah, that's hype for you, I guess.
Yeah.
But fortunately, when lots of people and lots of funders are involved, the chances are that there will be some sort of evolution. Fittest will survive.
And I would say the gentleman picked up perfectly on the microphones.
Okay.
So yeah, we caught that question straight away. Any other questions in the room? Please.
Hello, my name's Tim D. Williams. I'm visiting from the BCS ISG committee. I'm also former CSG listed advisor scheme member, so I've got that sort of background, cryptography, Royal Holloway, etc. So I've got a couple of very specific questions about potential mitigations for Shor's algorithm.
Yeah.
So I'm seeing people critiquing the need for the NIST lattice-based post-quantum cryptography algorithm as not necessarily the only potential solution to the problems of factorization. At least two other alternative propositions I've seen. One is that by limiting the periods of keys, that by doing limiting time exposure, you could actually solve much of the problem. So effectively, shorter public significancy key life cycles could be a potential mitigation, making quantum computing attacks uneconomical. And the other is potentially people looking at one-time pad distribution techniques, which obviously gives you potentially information theoretic perfect security. And recently I've been working with a chap called Adrian Neal, who's got a patented technology called QStream, which is specifically for distributing one-time pads. So I'd just be interested to know whether you would support the proposition that there are alternative methods of mitigating threats from Shor's algorithm.
There certainly are, but I would put it slightly more generally that there are routes that we can go down to mitigate the threats of quantum computing in general, and Shor's algorithm in particular. And you may have noticed I did have a bullet point that said, do we need public key cryptography at all? Yeah, I mean, hash-based cryptography, for example, is another mode of distributing key material. What I would say is that a point of view that's very prevalent NCSC and not so much on in the world at large is about costing. So one of the things that they would like is a good procedure for costing the attacks, and that it allows them to compute a sensible last date of use. The high-grade standard you want would be something like, will a medium-sized industrial country devoting 10% of its gross national product to solving this problem for the next 50 years succeed in reading one message? I mean, I agree it's impossible to do that anyway, but you'd like to have at least 2 data points on the graph before you try and answer that question. So yes, I would say that a combination of techniques, but this is what standards organizations are good at. They argue and they fight, and then they usually come up with sensible responses. And I think we will, I mean, as somebody said when we were talking about why don't we just use million-bit RSI? No one's going to build a million-bit quantum computer for 50 years, surely. Well, how do we know? I mean, if you can guarantee that's not going to happen, really. So, yes, there are more ways of skinning this particular cat. 50% chance.
Any other questions in the room? So I suppose my question was going to be around the similar vein, asking what other games might be in town, but with no knowledge. So I wasn't going to ask for an opinion on alternatives. I was merely going to ask a lot of the developments you mentioned, particularly these ones around the hidden structures. These were all in the vein of error correction, if I understood.
Well, that's the theme. The two sort of modalities there are error correction on binary binary vector spaces, and error correction or learning with errors on lattices, which are discrete.
So my question would be, are there any other paradigms?
Certainly there are. Probably the third interesting one is multivariate quadratic equations. The way that NIST tackled this was to announce something which was not a competition at all, but was something sufficiently much like a competition that it's a thing you can win. There were 70 plus entrants to that competition, which meant that each of the competing proposals had 70 other people desperately looking for an attack on them to make sure they wouldn't win. So that probably generated more serious attention than just publishing a paper and saying, here I've proposed a crypto system. What do you think? The chances are very high that no one would seriously. There is no academic reward mechanism really that rewards you for finding flaws in other people's crypto systems. It's hard even to publish that as a paper. But by folding it up into a competition, they did generate a lot of energy around that. So, and some of the 70 plus things were far out, but the majority were in the vein of lattices, error correcting codes, or complex quadratic equations, complicated quadratic equations.
Okay, thank you. Any other hands from the room? George.
Yeah, so the first possible solution that you proposed was where a qubit would be sent across the network in either the sort of cross state or the X state. I mean, first of all, I love that as a solution, and it really made me wonder why I never thought before. But because I've thought about this before, interest of mine. Why doesn't this work, or what are the problems with this? Because I'm like imagining this in my head, and it seems like a fabulous solution, but naturally it can't be, because otherwise they would just stop. So what are the issues with this?
Well, I guess one issue is re-engineering all the fiber optic cables and repeaters to you might have to do that anyway. But I think the quick answer is I don't know. I mean, it works in, like so many things, it works in theory, but it doesn't seem to be practically competitive. I don't know. The other thing is that it works. I mean, there was a time when fiber optic cables were so new and so wonderful that they were the answer to everything. Everything was about fiber optics. Now, this week, it's satellites. The polarized light solution doesn't work very well for satellites. Yeah, I don't know. It's there are quite interesting classical solutions which go back a long way, but no one really has taken them up.
I mean, we've got deathly silence on Zoom, but I have repeated in chat that Zoom participants are very welcome, and I am watching the open questions. Are there any more from the room?
I can ask one more. You mentioned about quantum key distribution.
Yeah.
As not being a favoured technology by NCSC. I completely agree with that. But I just wondered whether anyone was actually looking at the exceptionally high costs associated with this. I give a number: 10 megabytes per year for €1 million is what the European Space Agency are quoting to early subscribers. What kind of entities could possibly be in the market for such expensive technologies?
Well, the quick answer is I don't know. It's quite possible that people who are, financial institutions have an interest in very secure but also very, very fast communication between stock markets. They're spending other people's money.
So if it's not low latency trading, there's probably not many people who are taking it.
And I guess that's sort of at the extreme, at the other extreme end, there are things like nuclear command codes where, they've just got to work. They've got to not be, they've got to be secure. There's no, the cost of not being secure is infinite. But I just emphasize, I don't speak for NCSC. If they've changed, they might have changed their mind today. I don't know.
Okay, one more. Do you have any vision for what trends are likely to predominate in this area over the next few years? I'm not putting a particular time frame on it, but do you have a feel for what's going to be a predominant theme?
I think what we're seeing underneath some of the very excitable press releases is a war, let's say a rivalry between not just companies, but between technologies. There are multiple technologies for instantiating quantum bits, quantum circuits. The people who can successfully argue that their technology is better, faster, whatever, than others will presumably scoop the pool. So I think it's going to be at the technology level. The error correcting code, of course, depends on the technology, because it depends on the sorts of errors that you're going to get, but it's somewhat agnostic to the technology. So I think it's going to be around who can persuade the world that their technology is winning out. But then there'll be presumably a sort of feeding frenzy around the one that seems to be winning. Whereas, a company like, say, there are companies that just do build quantum error correction. They don't care what the technology is. They presumably will.
So it's almost like a technology style war that's going to occur, a bit like.
Would be my guess.
Yeah.
And as to which is going to prevail, I don't know. I mean, there is at least one technology which it's not a technology, it's a physics, which I think is failing to gain traction. There's, I think, serious question about whether Majorana particles even exist, let alone whether they could be made the basis of a quantum computing technology. But I may be wrong about that.
Very much.
And we do now have a question coming through cyberspace. And I think now that I've clicked answer live, others on Zoom can see that. So the question is from Xin Wan Chen. And this question is, how will quantum computers revolutionize our ability to model and simulate complex systems that are currently impossible or prohibitively expensive with traditional computers?
I think the likely area in which application domain is going to be, I think I already mentioned, it's going to be in drug discovery, protein folding, and other modeling biological processes, because the ability to understand, simulate, and experiment in silicon with biological processes is something drug companies have been after for a very long time. Of course, the competitor there is something like AlphaFold, AI techniques for modeling proteins. I'm not equipped to say whether either of those work very well, but the I think, yes, modeling of biological systems at cellular or metabolic level is, it's going to be huge.
We've got another one in chat. This is actually a closed question, but I think it leads on. So the question is, would the speaker, Richard, care to comment on supply chain, quantum readiness and technology vendor responsibilities to proactively plan for quantum readiness? So would you care to comment on such a thing?
Well, like, obviously, it's important. We have whole institutions whose job it is to look at that. So what was the supply chain would fall under the protection of national infrastructure. Yes, I mean it's hugely important, but it's something that you have to build at the national level. Because security and safety and all those other good things are costs, and they have to be. Somebody has to make you incur those costs, because otherwise you won't. Because companies drive out costs whenever they can.
Fantastic. So those are the only two I've had online. Did that prompt any more from the room? We're still okay for a couple of minutes if there are any final questions. Oh, hi, sorry, I didn't see the hand. Please.
I was very curious if quantum computing can facilitate like AI model and AI development.
Great question. I wish I had a great answer to it. It seems to me that the fundamental operation of learning, training a neural network or whatever on data is about optimizing a certain reward or loss function. But typically it seems that one has to have millions, billions of weights. So we're optimizing over a number of variables, which is far higher than the number of quantum bits that anyone could possibly imagine building in the near future. I think that there may be convergence of research to make neural networks, language models, a lot smaller, sparser, whatever, and it may meet the technology for using quantum devices to optimize specific loss functions somewhere. I think there could be a convergence, but at present all I can say is the possibility exists in principle.
Okay. Is there any final questions from the room?
Go on, I'll ask a question.
Thank you.
So a couple of years ago, I was looking at a course on quantum computing, and slide 2 said, this course requires no knowledge of particle physics. Slide 9 said, let's consider Schrodinger's equation, right? So my question for that is, how do we modify education of programmers and computer scientists? Are we always going to need specialist skills and knowledge of quantum theory and quantum physics before we get people who are able to program these new systems, or are we going to be able to introduce it into sort of general computing courses and have general purpose programmers involved in this? Because the programming style, certainly at the gate level, is so different that it's hard to see how they can be compatible. So it's how do we get a cohort of people who can actually program those things?
I think part of the answer is to, I don't know exactly how you do this, is to move away from a notion of computer science as being about programming and a notion of, towards the notion of it being about computation. That may be provocative, but if you're teaching people, your students, something that they have to unlearn to engage in quantum computing, what were you teaching them in the first place? To encourage a mindset in which it is possible for people to acquire the understanding of some particular mode of computation without believing that the one that they were first exposed to was the one true and only model. However, how you do that is not something I know the answer to. I can give you my answer, which is when I was a student, which was quite far back in the previous millennium, you couldn't study computer science as a degree subject in most universities. It was a one-year add-on to mathematics or physics or chemistry or whatever. I felt that it may not have done me too much harm, the fact that I couldn't do a degree in computer science, but that I had to learn other things as well. I did do a year's computer science, but only a year. So perhaps by doing other things, I acquired, I don't know, resilience isn't quite the right word, that's just openness to other things that.
There's a whole new different set of skills.
Yeah. I mean, it seems very likely that all forms of compute-related technology are moving very quickly. AI, quantum, openness and adaptability, more important. Direct technical knowledge of something that is already out of date. I'm conscious that may not, although that may answer your question formally, it may not actually be a helpful answer. It's the best one I've got.
I think it's a very good question.
How
that's going to happen in the future? Yeah. How we're going to actually keep.
And perhaps an answer to the question is: we want a diverse workforce with lots of different backgrounds, lots of different trade, in the hope that at least somewhere in there will be the ones that we need.
Okay, it is 20:59. Thank you to all the questions in the room. And thank you very much to Richard again for his talk and those answers.